Log on, tune in, find out. Another good idea from Cambridge.
Please. Thank you.
Okay, so the first thing is I would like to thank the organizers of this conference and our chairman session and everybody here and for the opportunity to come to speak to you and discuss and say something about my recent work. And this is a collaboration, some results, latest results obtained together with Dr. Guha and Gonzalez. These two are from the Air Force Research Lab in the US, and also Dr. Sheng from University of McCall. We just discussed a little bit about linear algebra problems from here. Pretty interesting. And this project, this is a small part of a big project, and it's supported by the Department of Defense and Air Force Research Lab. So if you ask me more questions, I may say no, I don't know. And but at least the talk was approved. So otherwise I cannot say it. But it's a very simple talk. And one of the reasons is Ari told me that your talk is on Thursday. So I guess that we had lots of intensive talks. So today, be relaxed. So we talk about computations of optical beam propagations from a different angle, which is different from the rest of the discussions. Well, highly oscillated wave problems. This is the optical problem, of course, highly oscillated. We know that optical waves has two kind of features. One is the particle features, the other is a highly oscillated wave. So let's look into the wave problems and see what's going on here. And of course, optical waves, we know that Schrodinger equations or other equations we mentioned in the past few days are very sophisticated. Even we reduce them to linear and still can solve them nicely sometimes. So makes it simple because my talk is about just one idea. So let's just look into this linear problem Helmholtz equation. And here be careful that this z is not time. That's different from the rest of the talks. Z is the direction of light propagation. And x, y are the dimensions perpendicular to z. That's it. So it's not time. But of course, you can view this as something similar to time. So let's look at equation 1, which is very simple, linear, and this kappa is a wave number related, of course. And this is nominal. If we write things in that way, engineers, they like to write in this way, and that's the wavelength. Okay, for optical waves, that's very small, you know. And in our discussions, in our case, this kappa is roughly around 10 to the 6, that kind of measure. Why? Well, many people look at the 10 to 2, 10 to the 3, and for engineers, they say that forget it, because it's very easy to solve. I use standard finite difference method implicit. But it's a large computations. So what? Because computers are big enough. Even like UT, they have a Ranger. That's big computer, several thousand processors. Just in seconds, you solve the problems. Okay, so we look into the problem to 10 to 6, maybe higher. Depends on the light you use. And see what's going on here. And the background is this kind of my research is related to advanced materials sciences. And the materials certainly basically is related to like nanomaterials and the composite micro lens. In other words, you build a lens which is very small, but you use composite with 1 million lens together. What's the effect? And you want to solve equation for each length. There's 1 million lenses over there. How to do that? And every equation 2-dimensional here. How about 3-dimensional? And how about nonlinear? Very easy, 8,000 terms over there. 8 other terms there, nonlinear. This is just an idea, simple linear equation. So our idea is we try to make things simple as far as engineers can use, can understand, that's success, and that's the funding. Okay, let's go ahead, look at the approach. So our idea is not new, actually. We want to look into the corresponding Economic equations mentioned by several speakers today, actually. That's a Greek word. It's not name, not a name for a person. Of course, we know that's a ray equation. And this equation, it's a very simple classical things. But surprisingly, it leads to the Fermat principle in mathematics, in PDE, and go all the way to Hamilton-Jacobi equations, which leads to $1 million problem if you want to try. It's simple. It's simple in any way. So let's go ahead and look at what's the approach people are using in physics. Well, in physics for engineers, they say that's very easy. We compute the beam propagation. Since this is an intensity function, this is wave functions. So I'll write this basic the optical wave function into the form u times exponential I omega function. Oh, well, x, y, z over there, they are functions, and of course, u is the amplitude of the light, of that intensity, and that omega function, people call this as a phase function. Of course, that's standard physics, classical, especially in geometric optics. Well, for convenience, let's just rewrite this into that true form. That makes it easier for us. So substitute this into the equation, Helmholtz equation. Let's see what's happened. Very simple, just calculus. And we derive immediately a pair of equations, coupled equations. What's wrong here? Well, you have the linear equation, right? And once you do this kind of transformation, this is nonlinear. Why nonlinear? Just AB, but AB things are here. We got a singularity here, U is in the denominator. But no problem, don't worry, that's the amplitude of light. And especially this equation used in somewhere near focus of the light. So don't worry, it's not zero, never be zero. Otherwise there is no light. So that's the coupled equation people obtained. That's not new, unfortunately. And these two equations have been used in optics for many, many, many years. Many years. Okay, so based on that, see what can we do? So that's exactly what I said. Look into the same problem from a different angle. See what are the things in front of us. Okay, look at B3 and 4. With those functions over there, nonlinear, but we know that no singularity. Okay, so but remember that kappa is a big number. That's the key issue. Well, think again. 3, 4 are equivalent to number 1, the equation we just had before, because we didn't throw away anything. Well, if they are equivalent, why are you looking to 3 and 4? Don't go to number 1 equation. We have so many methods for that. Fourier method, and the spectral method, and other methods, multiple scales, all kind of discussions. Why don't you use that? Okay, the problem is that 3 and 4, this U and the V, of course, not oscillatory, not. How can you amplitude the oscillatory? No, they are not oscillatory. Well, that wave number is bigger. Now the solutions U and the V are not oscillatory. Well, maybe I can try it. To solve that 3 and 4, see what's happened. Are there people did that before? Yes, there are people working in that way, and most likely physicists and engineers. So let's go ahead and see what's happened here. So rewrite that equations, coupled equations into just a system form. So by introducing that notation, so you can write things in that form. Now for any fixed A and a B, of course we know the matrix is skew symmetric. That's very easy. A skew symmetric, that's good property for us because we know the norm, the spectral radius, all these things are very easy to compute. Properties are obvious. So okay, so now make things even simple. Let's look into those traditional conditions, initial conditions and boundary conditions. That's simple enough, cannot be even simple. Of course, you say I can introduce in real applications, in the real projects, the equations are not that equations, more sophisticated, with nonlinear terms. Conditions are not those conditions, non-local conditions, but just say idea. So let's use those things. Very simple. But still afterwards, problem. Still problem, even though those simplest things we use. Go ahead. What to do now? Well, we just follow the standard engineer's way. And we look into splitting methods. Every numerical analyst knows that. Classically, we have two split schemes. One is called ADI, the other is LOD. Are they the same? They are similar, but they are different. But they are the same in the sense that both of these two approaches, ADI and LOD, can be written as exponential splitting. In that form, they are the same. Otherwise, they are different. Of course, this is if we know the history, we know that ADI basically started by Peaceman Richford, Douglas Richford, and these three people in the States. And LOD is different in Russia. Two sides, and did the same thing. That's in history. But anyway, that's traditional. Well, the approach is very easy. So we rewrite that coupled system into ADI way, LOD way. And be careful, this is XY, this is XX. Okay. Well, you may say, okay, you can do that. You can do that, suppose. And what's next? Next is okay, discretization. If we do that, why we can do this kind of discretization? Don't worry about the mesh or these things. Finite differences here. And why finite differences? All the engineers use finite differences whenever possible. So let's just stick into the old method. Simple idea. So do that. This is standard central finite difference in space. Of course, uniform step sizes are used. You can use non-uniform, but it will be different. But we don't want to make things complicated. So look at simple things. Okay, so once this is done, substitute this into the equation, throw away the truncation error terms, so you obtain system here, system here. That's not a big issue. But these things can be, with that discretization, and can be viewed as basically Paddy approximations of exponential splitting formulas. But look like they're first order splitting, but they're not. They're second order splitting actually. Why? Because we know that for splitting methods, ADR method, let's say that if we do X direction, Y direction next, and next step in reversed order, it gives you a strong splitting. So last time I met Gilbert Stronger, I asked him, I said, Douglas, these people at Richford should knew your method a long time ago, because a strong splitting just a reverse order of first order splitting. And he laughed. He said, yeah, they didn't realize that this matrix operation is actually the Paddy approximation of the exponential function. If they knew it, they wrote it out. But it actually is true. But anyway, so that's we use that formula will be enough. That's why ADI, LOD, enough. Second order. Second order, that's the maximum for the order of accuracy. We know that. Okay, so we have that basic scheme. And those matrices, we can rewrite this into a typical matrix forms of the systems. Well, the problem starts here, not before. Before everything's smooth, should be straightforward for us. So let's look into the 13, 14. That's the system. And the 15, 16, that's another system. What are the problems? The problems with that, we know the Paddy approximation first order splitting. Okay, that's easy. But the problem is what is that M? What is that M? Two matrices, block matrices, block tridiagonal matrices. And this each block is the little m we mentioned before, which can be skew symmetric. Now, let's come back. Seems we can explicitly write out these matrices. Let me just roughly express here. And this is a typical matrix by using the homogeneous first boundary conditions. And if you use a second boundary condition, the Neumann condition, and the first two terms will be different, right? Oh, that's basic for numerical analysis. Okay, basic, fundamental. Anyway, I have all those matrices generated. I can explicitly write all these things. So, next thing is how good those systems can be. Can I solve them nicely, or just they collapse? Why so many smart people don't use this kind of method? Is that a problem? Why are you sticking to very complicated procedures, not those simple things, one page over? My question. So, okay, let's go ahead and look at the systems, good or bad. So, go ahead by introducing a few notations here. And sorry about here, I just forgot to write out some definitions. And the matrices T I mentioned here is we notice that, maybe it's too low. The matrix M, say, we use that, can be decomposed into ST. And this here, S is a diagonal block matrix, and T is a tri-diagonal block matrix. You can easily see that. So M is that, so you can write S N also in that form, let's say 1, 1, 2, 2, with similar features. So the rest of the theorem is based on S and the T, because that's relatively easy to prove certain properties. Okay, go ahead, do that. So next thing is just a linear algebra. Everybody knows that. And go ahead, do that decomposition, and step by step, and you find that these two matrices, M and N, similar. Well, that's of course we know that it's constant coefficient problem. Similar. And then we prove certain results. Okay, and this is the norm for the gamma matrix we just obtained, which is part of decomposition. And obtained for that, and we are happy, very happy to see something like kappa in the denominator. Why? Kappa is a big number, we said 10 to the 6. If the size of the matrix involved are pretty small in that sense, we have a good future. So go ahead, look into further the properties of the M and the N matrix, and pretty easy to show that the spectral radius is big O, O1 over kappa. And actually here we saved is the dimensional Cora number. But that's basically it's a bounded positive number, so that's okay. Kappa is bigger. Here we take advantage of the HOP. Without that, we can be in trouble. Okay, so go ahead. We go further to show these matrices. Here, and this MN hat matrix are linked to these two matrices in certain way. And we may define different norm for it anyway. So, okay, so continue the exploration. And we look into these two matrices. The two matrices are inside that implicit scheme and the pair approximation. And be careful. In the classical discussions of implicit method, like such as Clark-Nixon method, if these two N and M are the same matrix, that's a piece of cake. That's obvious. But now these two matrices are different. Look at that. So this is not a pair approximation of a simple exponential matrix. Question, what is that? Is that matrix bounded in 2 norm, in spectral radius, in L1 norm, in whatever norm you want, but just matrices? Can you do that? It turns out, yes, but not easy. Not that simple. actually. Do it, not EB. And what I said just now is that this M and N are similar. Similar, even that P, that transport matrix, we can find it exactly. Not too complicated, but not trivial. Okay, so the rest of the work here is try to show that indeed these things are bounded. And we can show that so far, A square, B square, so far, unfortunately, these two things are bounded by this part. And mu and eta are two-dimensional Cora numbers. So these are two bound numbers. But the denominator is very good. And of course, if the denominator is 1, and that's disaster. Basically, the method is not good at all. So don't use it. But now, very good. So roughly, we can show that that the result is not easy to arrive at that part. But this is not too known of A and B. Otherwise, we have to look into AT. You see, and so still struggling with all this kind of a very basic matrix eigenvalue problems actually so far. But the future is good. And last night I talked with Dr. Sun in Macau. Well, he's just struggling day and night. We try to find out precisely. We want to show we know that it's true. There's two known of that matrices AB are bounded. And with that K, a single K in the denominator, because all the experiment shows that. And if we can show that, that's great, because this is exactly the method for optical problem, but not necessary for other problem. Okay, and also recall in the very beginning, I said that this is a project run with the DoD. So the engineers, they want efficiency. And this is with the material development. I just mentioned the micro lens, the matrix of macro lens, and the other side is negative index materials. Everybody knows that. So those things are very important. They want to see the result. They want to show me that focusing happens with that method. Okay, so in that sense, we have to reorganize our scheme, see if it's efficient. It's easy to use by engineers, non-mathematicians. Yes, it turns out very easy to do that. So you just regroup the algorithms in the 4 steps with the matrices built in, and also good thing that matrix is once you have that, it's fixed basically. So in 4 steps, I solve ADI. In 4 steps, I solve similarly LOD. At second order, every time you exchange X first, Y next, next time try Y first, X next. Do it. You have very good accuracy. Simple. Everybody understands. So once I have this formulation, continue to do that. This is a LOD. And let me show you just a few slides, just from this particular example, not a real example. Okay, so this is an illustration. For illustration, here we use a pretty small this carbon number. I think the carbon number used here is just 10, pretty small. Otherwise, it's a very narrow area. You have to enlarge, because oscillate a lot. You have to enlarge into a very small region that can see the same thing. So we do the calculation, compute that wave number, that function, and in the form of U and V. But be careful, the solution of Helmholtz equation is complex. Here we're not doing the things people are doing to decompose that complex function to real imaginary part. We're not doing that. We're doing the thing to decompose that function, wave function, into amplitude and phase. So very easy. You compute those functions, and this is based Gaussian bin data input, just like use the 1-dimensional in the morning. It's a 2-dimensional, same thing. No big deal. And they decompose, and they do the computation step by step, and every time that system we just mentioned, very easy to solve. Because why? Those functions are very nice functions with waves. Amplitude, right? The change doesn't change too much. And those phase functions, right, will not dramatically change either. So you just compute, and so far the systems we obtained is very numerically very stable. You can run this just forever for a few hundred steps. Actually, the engineers only need that. They don't need go further forever. Stop a few hundred steps and recompose. Right? You can once you have the unit V after say 100 times or 200 times or 1,000 times iteration, and it recompose that the real wave function. That's highly oscillator. So when you do the computing, you never worry about oscillation. When you have the solution, you recompose them. Because this is wave, this is optical wave, we know it. It can be written that in physics. So that's just an idea here. So I'll show you a few pictures, a few contours, and there is a movie. I don't want to download it. It's pretty big. Also, there is some restriction inside. I don't want to do that. So pretty nice of me to show that. Here I just showed a few pictures up to 150 steps. It's a very good and stable solutions. And here just say a few words that this is a pretty nice picture from the lab. One of the things we did is a small drop of water, and use a laser beam penetrate that laser, that water, and see the effect afterwards. Any focusing, refocusing things, and we want to do that numerically. And use what? Use the method similar to I just explained a little bit. It's simple, very simple, but effective. Very fast. Okay, and the rest of things like numerical, like error estimates, all these things need to be done, but it should be should not be too hard as far as you have that linear system in hand. Okay, that's it. Thank you.
Any questions? Yes.
You did not mention the approximation of the nonlinear terms.
No.
Is this straightforward?
Yeah, also straightforward. Yes, there is nonlinear term, Schrödinger equation, 8 or more term. But the treatment will be a little bit tricky, depends on the situation you consider.
What do you do? Symmetric finite differences?
Yeah. And because here we don't need to use adaptation so far. It's a simple case. Adaptation can be used, but not necessary.
Any other question? Comment? Okay, if not, thank you again.
Thank you.